There is a small, quiet fact about your own body that almost never comes up, and tonight it happens to be the doorway into everything else. The bones holding you together, right now, under the warmth of the blanket, are not dry. They are not stone. They are not the pale, hollow scaffolding we tend to picture when we picture a skeleton propped up in a corner of a schoolroom. They are warm. They are threaded with blood vessels and living cells. They are being quietly rebuilt and dissolved and rebuilt again at this very moment. And inside the long ones, there is a soft store of fat that your body keeps in reserve, the way an old house keeps fuel in the cellar against a long winter. If you lie still enough and let your weight settle down into the mattress, you can feel the frame of yourself pressing gently into the softness beneath you, at the hips and the shoulder blades and the back of the skull. That frame is alive, and it is also, in a way that will matter a great deal before this night is over, a larder. Now take that same fact and make it very large. Somewhere out in the open ocean tonight there is a whale, perhaps a blue whale, the largest animal that has ever lived on this planet, longer than a tennis court and heavier than a fully loaded aircraft, moving through the dark water with the slow, economical rhythm of an animal that has never needed to hurry. Perhaps a fin whale, or a sperm whale, or one of the strange, deep-diving beaked whales that spend most of their lives far beneath the surface and are so rarely seen that several species are known mainly from bones washed up on remote beaches. Inside all of them, the same arrangement, a skeleton of enormous bones, and inside those bones, an extraordinary quantity of fat. And one day, after 50 years or 80 or 100, that whale will die. Most of them do it quietly, far from any shore and far from any witness, and the body will begin the longest journey it has ever made, which is straight down. What happens after it lands is the subject of tonight. It is not a small subject. When a great whale comes to rest on the deep seafloor, it does not simply disappear. It becomes a place. It becomes an address, a location that other animals travel to and settle on, and live upon, and reproduce upon. An entire small city assembled out of one body, and that city can keep running for decades, half a century. In the case of the largest whales, by the best current estimates, longer than many of the animals living on it, longer than most human careers, longer than the working life of the submersibles that go down to look at it. The flesh goes first, over months or years. The bones last far, far longer. And the reason the bones last so long is the same reason your own skeleton is warm tonight. There is fuel locked inside them, and it takes the deep sea a very long time to get it out. Welcome back to sleep, Abyssal. Settle in, let the room go quiet, and let the sea take the weight of the day. Before we go down, one gentle question, and you are welcome to leave the answer below whenever you like. Where are you listening from tonight, and how deep is the dark outside your window? It is a quiet pleasure to read them, and there is something companionable about knowing how many rooms this reaches, and how many different kinds of night. Here is the shape of the drift ahead. Tonight, we will follow one whale from the surface all the way to the bottom, and then we will stay. We will watch what arrives first, and what arrives after that, and what arrives so late that everything else has long since gone. We will look closely at a worm with no mouth and no stomach that eats bone by dissolving it, and which nobody knew existed until the year 2002. We will sit with the researchers who studied the first whale fall ever properly examined, in 1987, and consider the odd truth that almost nobody has ever watched one of these things unfold from beginning to end. And near the end, we will travel to a stretch of the southeastern Indian Ocean where, in the summer of 2026, a team in a submersible found something that changed the scale of the whole idea. Nothing here is frightening. There is no menace in this story, no matter how it might sound at first hearing. What is actually happening down there is closer to composting than to anything else. And if you have ever turned a compost heap in a garden and felt the warmth come up out of it, you already understand the essential principle. Something ends. A great many other things begin. The deep sea is patient and thorough and quite without opinion about any of it. If you find it easy to drift off here, a quiet like helps others who are looking for the same calm to find their way to it. And that is all. Now, let us go back down. Start at the surface then, because everything begins there. Picture a stretch of open ocean far from land. The color is the deep, saturated blue that water only reaches when there is nothing beneath it for miles. A blue with a kind of weight to it, almost purple where the swell rolls over. The surface is moving in long, slow hills rather than waves, the way the open ocean usually moves when the wind is light and the whole thing rises and falls with a rhythm that is closer to breathing than to anything mechanical. Above, a high sky and a scattering of thin cloud. Below, 4,000 meters of water, which is to say 2.5 miles of it. Straight down, cooling and darkening the whole way. And on the surface, a whale that has stopped moving. We do not know very much about how whales die. It is one of those gaps in our knowledge that seems impossible until you think about the size of the ocean and how little of it anyone is ever looking at. Some are taken by predators. Some strand on beaches for reasons still being argued over. Some are struck by ships, and some become entangled in fishing gear. And some, presumably a great many, simply grow old and their bodies eventually stop, out in open water, in the middle of an afternoon or the middle of a night, with nothing at all to mark it. What happens immediately afterwards is a matter of chemistry and buoyancy. A living whale is very finely balanced in the water, close to neutral, which is why they can hang motionless at depth without effort. A whale that has died begins to change. Bacteria that were always present in the gut continue their work, and one of the byproducts of that work is gas, and gas is lighter than water, so the body often rises. Not always, and not for long in every case, but often enough that floating whales are a familiar sight to anyone who spends time on the open ocean, lying at the surface with the back exposed, quietly swelling. At the surface, the first visitors arrive. Seabirds find it quickly, because seabirds find everything. Sharks come from a long way off, following a scent trail through the water in the patient, zigzagging manner that sharks use, closing the distance over hours. If the whale has died near a coast, the whole thing may drift ashore and become a stranding. And then the story goes in an entirely different direction, into the sand and the gulls and eventually the bulldozers. But out in the open ocean, away from land, the surface stage is temporary, because eventually the gas escapes. The skin is opened by the animals feeding at the surface, the swelling subsides, the body loses the buoyancy that was holding it up, and the balance tips the other way. And a whale that is no longer buoyant is a very heavy object indeed. Bone is denser than seawater. Muscle is denser than seawater. 100 tons of animal with the gas gone out of it has only one direction left. It goes down. And here is the first thing that surprises people when they hear it. It goes down fast. We have a tendency to imagine the sinking as a slow, drifting, feather-like affair, the body turning gently over and over as it descends through shafts of light. It is a lovely image, and it is largely wrong. A large whale carcass that has lost its buoyancy sinks with real purpose, at something in the region of a few meters every second, which means it is covering the distance at roughly walking pace, only downward. Estimates vary with size and condition and how much gas remains, but the general finding is that a great whale can reach 4,000 meters in an hour or two. It leaves the sunlit world and arrives in the permanent dark of the abyssal floor in less time than it takes to watch a film. So follow it down. The first 200 meters are the part of the ocean we picture when we picture the ocean. Light and plankton and the blue growing steadily deeper. The whale passes through it quickly. Anything still feeding at the surface loses it almost at once, because the descent is faster than most surface animals care to follow, and the body simply drops out of the lit world and into the one below. Between 200 meters and 1,000 is the twilight zone, the mesopelagic, where the light thins out from blue to a blue so dark it is hardly a color at all, and then to nothing that a human eye would call light. This is the busiest and least visited part of the ocean, a vast middle layer full of lanternfish and squid and siphonophores, and the great daily migration of animals that rise towards the surface at dusk and sink again before dawn, the largest movement of living creatures anywhere on Earth, happening every single night, mostly unwitnessed. The whale passes straight through the middle of it. Some of the animals there will register the passage as a pressure wave, a disturbance, a shadow going by. A few may follow for a while. Most will not. By 1,000 meters, the last of the sunlight is gone, and gone is the right word rather than dim. Below this depth, the only light in the ocean is light that living things make for themselves. And there is a surprising amount of it. Brief blue-green sparks and flashes and slow pulsing strings of light, but it is scattered and momentary, and it illuminates nothing. The water here is cold, somewhere around 4 degrees above freezing, and it will stay at roughly that temperature all the rest of the way down. The pressure has already risen to about 100 times what it is at the surface. The whale, being made largely of water and fat and bone, does not particularly mind. There is very little air inside a body at this stage, and it is air that makes pressure a problem. Solid tissue simply passes through unbothered. 2,000 meters. 3,000. The whale falls through the bathypelagic, the midnight zone, a layer of ocean so large that if you took every other habitat on the planet and added them together, all the forests and grasslands and deserts and rivers and the sunlit ocean above, they would still not match it. It is the single biggest living space on Earth by an enormous margin, and it is almost entirely water. The animals in it are thin, small, slow, patient, and widely spaced, because there is not much to eat. That last point is the one to hold on to, because everything that happens later depends on it. At around 4,000 meters, the whale meets the bottom. It does not crash. There is no cinematic impact, no plume of sediment blossoming upward in a great cloud, or at least not much of one. Water is dense, and it resists, and the last part of the descent is slower than the middle. What happens is closer to a heavy settling, a long, soft arrival, the body meeting a floor of very fine sediment and pressing down into it, and a low haze of disturbed particles lifting a meter or two, and then beginning, immediately, to settle back. Within an hour, the water is clear again. The whale lies where it landed, usually on its side, sometimes on its back, one enormous flank rising out of the sediment like a low hill. And then, for a little while, nothing at all happens. This is worth sitting with, because it is the quietest moment in the whole story. 100 tons of the richest food source in the deep ocean arrived out of nowhere, lying in the dark on the abyssal plain, and for the first hours there is simply silence and cold, and the slow drift of a current that moves a few centimeters a second. Nothing has noticed yet. The news has not traveled. To understand why what follows is so remarkable, you have to understand the floor it landed on. The abyssal plain is the largest single habitat on the surface of the Earth, covering more of the planet than all the continents put together, and by any ordinary measure it is one of the emptiest places there is. It is flat, astonishingly flat, flatter than any landscape above water, sloping so gently over hundreds of kilometers that if you could somehow walk across it, you would never once feel that you were going uphill or down. The floor is soft, a pale fine ooze made of clay and the microscopic shells of things that lived at the surface and drifted down after they died, sometimes hundreds of meters thick, accumulating at a rate of perhaps a centimeter every 1,000 years. The current is slow. The temperature does not change with the seasons, or with the years, or with anything at all. The dark is total and permanent, and there is almost nothing to eat. Everything that lives down there depends on food falling from above, because there is no sunlight, and therefore no plants, and therefore no growth of the kind that supports life on land or in the sunlit ocean. What arrives is called marine snow, and it is one of the loveliest phrases in oceanography for one of the humblest things. It is a continuous, slow drift of small pale particles, the leftovers of the world above, fragments of dead plankton and empty shells and fecal pellets, and scraps of gelatinous animals that fell apart somewhere on the way down, bacteria and mucus binding it all into loose flakes that fall at a few meters an hour, taking weeks to arrive, turning over in the current as they go. In a submersible's lights, it looks exactly like a snowfall in a dark field, drifting through the beams in every direction, including, oddly, upward. When a current catches it, it never stops. It has been falling for as long as there has been life in the ocean above, but it is thin. Of all the living material produced at the sunlit surface of the sea, only a very small fraction ever reaches the abyssal floor. Most is eaten and re-eaten on the way down, passed from animal to animal through the twilight zone and the midnight zone, until what finally arrives at 4,000 meters is a small percentage of what set out. Estimates differ by region and season, but researchers generally put it somewhere in the range of 1 to a few percent. The abyss lives on crumbs, which is why the animals down there are built the way they are. They are slow and small and long-lived and sparing with energy in a way that would look like laziness anywhere else, and is in fact excellent engineering. Sea cucumbers that graze the surface of the ooze with the deliberation of someone reading a book they have all week to finish. Brittle stars lying in the sediment with a single arm raised into the current. Grenadiers, also called rat tails, cruising slowly a meter or two off the bottom with enormous nostrils, sampling the water for any trace of anything. Amphipods, small pale crustaceans like woodlice, buried in the sediment. Waiting. Waiting is the abyssal skill. Everything down there is good at waiting, because on any given day nothing happens, and then a whale arrives. There is a calculation that gets made in this field, and it is the sort of thing that reorganizes how you think about the deep sea. Take the amount of organic carbon that drifts down as marine snow onto a given patch of abyssal floor in a year. Now take the amount of organic carbon in the body of a single great whale. The comparison is not close. A large whale carcass delivers, in one afternoon, roughly the amount of food that would otherwise arrive on that patch of seafloor across something like a century or two of ordinary snowfall. 100 years of dinner, all at once, in one place. The deep sea has evolved, over a very long time, an entire set of responses to precisely this event. Not to whales specifically, at first, but to the general category of the large windfall, the sudden concentrated bounty in a landscape of scarcity. And what follows on the seafloor over the next hours and days and weeks is one of the more organized things in nature, though it does not look organized while it is happening. It looks, if you were watching, unhurried and rather orderly. Things arrive in a sequence. They arrive because of what has arrived before them, and each group changes the whale in a way that makes it suitable for the next. The first of them are already on their way. The whale announces itself chemically, long before anything sees it. Within minutes of settling, molecules begin to leave the body and enter the water. Amino acids, mostly, and various small compounds that are the ordinary signature of animal tissue, dissolving off the surface and being picked up by the slow bottom current and carried away downstream in a long, thin, invisible plume. The current at 4,000 meters is gentle, often only a few centimeters a second, so the plume does not race off. It uncoils. It stretches out along the seafloor in the direction the water happens to be going, spreading and thinning as it travels, a ribbon of information laid across the plain. And the animals of the abyss are exquisitely good at reading exactly this kind of information. They have to be. In a landscape where food arrives rarely and unpredictably, and could be anywhere, the ability to detect a few molecules of something edible and then work out which way it came from is not a refinement. It is the whole survival strategy. The first to respond are usually the small ones, and there are a great many of them. Amphipods are crustaceans, related distantly to crabs and shrimps, and the deep-sea species look like pale, translucent woodlice, ranging from a few millimeters to, in the largest abyssal species, something closer to the length of a hand. They live in and just above the sediment in numbers that are difficult to picture, and most of the time they are doing very little. When a scent plume reaches them, they leave the sediment and swim into it, and they swim up the gradient, which is to say towards the stronger signal, adjusting as they go. From a kilometer away, this takes some hours. From further, longer. They come in from every direction that the current has touched, which over the first day means from a widening arc downstream, and they arrive in the thousands and then the tens of thousands. We know they do this because of a piece of equipment called a baited lander, which is one of the more charming inventions in ocean science. It is essentially a weighted frame with a camera, a light, a bait bag and a timer, dropped over the side of a ship and allowed to sink to the bottom on its own, where it sits and photographs whatever comes. Then a signal releases the weights and it floats back to the surface days later to be collected. Landers have been dropped all over the world's abyssal plains, and the results are consistent everywhere. Bait goes down. For a while, nothing. Then a single amphipod appears at the edge of the frame, then two, then the frame fills. And in the photographs from the second and third hours, there is often so much movement that the bait is no longer visible at all, just a slow silver-gray shimmer of small bodies. Then, over the following day, they disperse again, and the plane goes back to looking empty. That is the response to a fish head in a mesh bag. The response to 100 tons of whale is the same response, scaled up and stretched out across years. Behind the amphipods come the fish. Grenadiers arrive early, and they are worth a moment on their own, because they are among the most abundant fish in the deep ocean, and almost nobody outside the field has heard of them. The name refers to the shape, a large, blunt head, big eyes, and a body that tapers away to a long, thin tail, so that the whole animal looks a little like a tadpole drawn out to an improbable length. They swim with a gentle undulation, keeping a meter or so above the sediment, moving in a search pattern that has been described as methodical, which is exactly what it looks like on video. Their nostrils are large, and their sense of smell appears to be very good. When they encounter a plume, they turn into it and follow it home. Then the sleeper sharks, in some parts of the world, and the sleeper sharks are marvelous. The Pacific sleeper shark is a large, thick-bodied, unhurried animal that can exceed 4 meters, and everything about it is built for economy. It moves slowly. Its tail beats at a rate that has been measured at a fraction of a beat per second in some observations, which for a fish of that size is barely moving at all. Its close relative in the North Atlantic, the Greenland shark, is now thought to be the longest-lived vertebrate known, with individuals estimated at several centuries old, though the dating methods carry real uncertainty and the field is still refining them. These are animals that have taken the abyssal principle of waiting and made an entire way of life out of it. They cover great distances at almost no energetic cost, and when something large and edible appears on the seafloor, they are extremely well placed to take advantage of it. A sleeper shark arriving at a whale fall does not rush. Video and still images from carcass sites show them circling, approaching, drifting off, returning, taking their time over hours, sometimes several individuals together, in a manner that has almost nothing of frenzy about it. Slow, methodical animals working on a slow, methodical problem. They have a distinctive feeding action, a rolling motion of the head that lets the lower jaw cut a clean circular section out of soft tissue, and the marks they leave on a carcass are correspondingly neat, round, and scooped. Then, sooner or later, the hagfish. Hagfish are one of the great oddities of the vertebrate world, and one of the oldest lineages still living. They look like eels and are not eels. They have no jaws, no scales, and a skull made of cartilage. Their skeleton is a simple rod running the length of the body rather than a spine of separate vertebrae. Their eyes are reduced to pale patches under the skin that probably do little more than distinguish light from dark, which in their world is not much of a loss. They have 4 hearts. Their blood is at the same salt concentration as seawater, an arrangement almost unique among vertebrates, and one that suggests a very long, very old relationship with the sea. They live buried in the sediment, and they are already there when the whale arrives, sometimes in considerable numbers, sometimes hundreds in the area around a carcass site. What brings them out is the same chemical signal that brought everything else, and their sense of smell is excellent. They emerge from the ooze, they cross the sediment in a slow horizontal wriggle, and they go to work on the soft tissue with a rasping plate covered in horny teeth that pulls material inward with a motion something like a pair of curtains being drawn. They are also, and this is the part that has made them mildly famous, extraordinary producers of slime. A hagfish under stress releases a small quantity of material from glands along its flanks, and that material meets seawater and expands, within a fraction of a second, into an enormous volume of soft, transparent gel. The proportions are genuinely startling. A teaspoon of the released material can become several liters of slime almost instantly, threaded through with protein fibers that give it a fabric-like strength. It is a defensive measure, effective against gill-breathing predators, and it appears to be effective enough that hagfish have not needed to change their basic body plan for a very long time. To get out of their own slime, they tie themselves into a knot and slide the knot down the length of their body, wiping themselves clean. There is nothing else in nature that solves a problem quite that way. And then the crabs, which arrive later and stay longer than almost anything else. Deep-sea crabs come in several kinds, and the ones that turn up at whale falls tend to be the large, slow ones, lithidids in particular, the family that includes the king crabs. They are long-legged and heavy-shelled, and they walk rather than swim, which means they come from a good deal closer than the fish do and take considerably longer over the journey. A lithidid crossing abyssal sediment moves with the unhurried, high-stepping deliberation of something that has never been in a rush and has no natural reason to start. They are generalists, and that is exactly what a whale fall rewards. They will take soft tissue directly. They will take the small animals that have gathered to take soft tissue. They will work along the seams of a partly exposed skeleton picking at whatever is lodged there, and they will still be doing it years later, long after the fish have gone, because a crab can make a living from very little and sees no reason to leave a place that keeps providing. With them come squat lobsters, which despite the name are not lobsters, and which sit in crevices with their claws held out and their tails folded neatly underneath. Sea spiders, which are not spiders either, stepping over the bone on absurdly long, thin legs. Occasionally an octopus, which at these depths tends to be a soft, pale animal with fins on the sides of its head, settling onto a rib and staying there for an hour or two, apparently for no reason beyond the fact that a rib is a good place to sit. The sequence in which all this happens has been recorded at implanted carcass sites, and the pattern is fairly consistent. Amphipods within hours, fish within a day, larger fish over the following days, hagfish emerging within the first week and sometimes the first day, crabs within weeks, then a long plateau of everything at once, weeks turning to months, turning to years, with numbers rising and falling as conditions change, and then a gradual falling away. There is no moment when the mobile scavengers finish. They simply come less often and stay less long and eventually a camera left on the site records days at a time in which the only movement in the frame is a drift of particles and the slow flexing of a brittle star's arm. Between them, over the following weeks and months, these animals will remove most of the soft tissue on the whale. Researchers call this the mobile scavenger stage, and the name is precise. Every animal in it moves. They come from elsewhere, they stay while the resource lasts, and they leave. The rate of removal has been estimated from carcasses that were deliberately placed on the seafloor and revisited over time, and the figures give a sense of the scale. Somewhere in the region of 40 to 60 kilograms of tissue can go in a single day. That is a good deal of whale. It is also, when set against a body of 80 or 100 tons, not very much at all, which is why this stage does not last weeks. It lasts months. For a large whale, in cold, deep water, it can last years. There is no hurry in any of it. This is the part that is hardest to convey, because the words we have for animals eating tend to carry speed and violence in them, and what actually happens at a whale fall is closer to erosion. Cold slows everything. At 4 degrees, metabolic processes run at a fraction of the speed they would at the surface, and every animal involved is operating in energy-saving mode as a matter of routine. A time-lapse film of the mobile scavenger stage, if anyone had ever managed to make one across its full length, would show the shape of the whale changing over months the way a snowdrift changes over a warm week, softening and settling, and losing its outline, with the great flank sinking lower against the sediment, ribs beginning to show through, first as ridges under a smooth surface, then as an outline, then as themselves. And around it, on the sediment, the second stage is already beginning, because the first stage has been making a mess. When a large animal is being taken apart slowly on a soft floor, not all of it goes into the animals doing the taking apart. A great deal falls off. Fragments of tissue, fats, fluids, particles too small for anything to bother chasing, all of it drifting the short distance to the sediment and settling into it, along with the waste products of every creature that has come to feed. The result is a ring of ground around the whale that has become, in a few months, the richest patch of seafloor for a very long way in any direction. It shows in the sediment cores. Researchers who have sampled the ooze beneath and around implanted whale carcasses find organic content far above the background level of the surrounding plain, and the enrichment extends outward well beyond the body itself, several meters or more in some measurements, fading with distance the way warmth fades from a stove. The color changes. Abyssal sediment is normally pale, a soft gray or fawn, and enriched sediment darkens, sometimes to a deep gray or black in the layers just under the surface, because the oxygen in it has been used up and the chemistry underneath has gone anaerobic. And into that ring, in numbers that are difficult to credit, come the small things. This is what researchers call the enrichment opportunist stage. And if the first stage belongs to the large and mobile, this one belongs to the small and abundant. Its residents are mostly animals that live permanently in and on the sediment somewhere in the region, in low numbers, getting by. Given a sudden and enormous supply of organic material, they do what small animals with short generation times do everywhere on Earth. They multiply. Polychaete worms lead the way. Polychaetes are the segmented marine worms, an ancient and immensely varied group, and the deep sea is full of them in forms that range from the plain to the frankly ornamental. On and around a whale fall, the numbers can climb into the tens of thousands per square meter in the most enriched patches, which is an astonishing density for the abyss, several orders of magnitude above the background. Certain families turn up again and again at these sites, particularly the dorvalides, small pale worms only a few millimeters long that appear to specialize in exactly this kind of temporary organic bonanza. They are found at whale falls, at wood falls where a sunken tree has come to rest on the seafloor, and around natural seeps of organic material, and it is thought that this ability to find and exploit scattered rich patches is their entire way of life. With them come snails, tiny and thin-shelled, grazing on the bacterial films that are beginning to spread across every available surface. Cumations, small hooded crustaceans that plow shallow furrows through the top layer of ooze. Copepods in vast numbers, most of them a millimeter or less. Various bivalves. Nematodes, the microscopic roundworms that are present in essentially all sediments everywhere on the planet, and which respond to enrichment by becoming even more present than usual. And bacteria, which by this point are the quiet majority partner in everything that is happening. If you could look at the whale fall now, some months to a year or two after the arrival, the scene would have changed considerably. The clean outline of an animal is gone, What lies on the sediment is a partly disarticulated skeleton, still with a good deal of tissue attached in places, particularly around the skull and the heavier joints, with ribs separated and fallen outward, and vertebrae beginning to work loose from one another. The bones are no longer white, if they ever were. They have taken on a mottled look, patched with pale films and darker stains. The sediment around them is discolored for several meters in every direction, and it is soft and disturbed, and if you shone a light across it at a low angle, visibly worked over, printed with tracks and furrows and small holes. Around the edges, in the still water, there is a faint haze of particles that never quite settles, because something is always stirring it, and the whole assemblage is now supporting a number of species that puts it in a category of its own. When researchers went carefully through the animals living on and immediately around a single whale skeleton in the Santa Catalina Basin off California, they counted more than 12,000 individual animals from more than 40 species of the larger, visible kind, and that was before the microscopic fauna were considered. Across whale falls examined in the Northeast Pacific as a whole, the recorded species list runs into the hundreds. For a habitat that is essentially one dead animal lying on an otherwise thinly populated plain, that is a remarkable concentration of life, and it is on a par with the richest deep-sea communities known. It is worth pausing on how strange this is when you set it against the surroundings. The abyssal plain is not lifeless, but it is sparse, and it is sparse in a very even, unvarying way. Everything is spread thin. A whale fall is the opposite of thin. It is a dense, crowded, chemically active island of activity, sitting in the middle of all that emptiness, visible on sonar sometimes as a small, bright anomaly on an otherwise featureless floor, and it will remain there for a length of time that has almost nothing in common with how long the whale took to arrive. The stages, incidentally, are not really stages in the sense of scenes in a play, one ending before the next begins. That is how they were first described, and the sequence is real, but the boundaries are soft and the overlap is extensive. Mobile scavengers are still visiting a carcass while opportunists are colonizing the sediment around it. The chemistry of the third stage, the one we have not reached yet, is already starting deep inside bones that still have flesh on the outside of them. Different parts of the same whale can be in different conditions at the same time. The skull, dense and heavy and full of oil in some species, behaves quite differently from a rib. A vertebra half buried in sediment goes anaerobic much sooner than one lying in the open, so it is better to imagine the whole thing as a set of overlapping waves, rather than a staircase. Each wave rises, while the one before it is still falling. The whale is being taken apart along several timelines at once, and underneath all of it, the timeline that lasts longest is already running. Because the animals that arrived first, for all their numbers and all their appetite, could only reach what was reachable: soft tissue on the outside, muscle, blubber, viscera, the enormous quantity of accessible material that made up the greater part of the whale by weight. What they could not reach was inside the bone. And the bone of a great whale, as we said at the very beginning of tonight, is not a dry structural material. It is a store. Whale bones are unusually rich in fats. Bone in general contains lipids, in the marrow and threaded through the mineral matrix itself. But in the large whales, this reaches proportions that have genuinely surprised the people who first measured it. In some skeletal elements, the lipid content is a substantial fraction of the bone's weight, high enough that whalers of an earlier century boiled bones as well as blubber and got a useful oil out of them. The skull and the jaw of a sperm whale, the vertebrae of a blue whale, the heavy bones at the base of the flipper, all of these are, in effect, tanks, sealed tanks. That is the important part. The mineral structure of bone is a poor conduit for water and a poor place to be a bacterium, and the fat inside is not sitting in an open reservoir waiting to be poured out. It is locked into a hard, porous matrix that is very difficult to get into, which is why, after the last hagfish has left and the last sleeper shark has moved on and the sediment has begun, slowly, to return to something closer to normal, the whale is not finished. It is barely a third of the way through. What comes next is slower, quieter, less visible, and it goes on for decades. It requires no teeth, and it runs on a chemistry that is, in a way that took the scientific world some time to appreciate, exactly the same chemistry that powers the strangest and most famous ecosystems in the deep ocean. To get there, we have to talk about what happens when fat is broken down where there is no oxygen. Everything alive needs to get energy out of something, and the usual way of doing it, the way your own body is doing it right now as you lie there, is to take a fuel and combine it with oxygen. The fuel can be sugar or fat or protein. The oxygen comes in through the lungs. The two are brought together in the cells, and the energy released is used to do everything else. It is efficient, and it is nearly universal, and it is the reason that oxygen is the single most important substance in the air. But it is not the only way, and it has never been the only way. There are bacteria, ancient ones, from lineages that were established long before there was any appreciable oxygen in the atmosphere at all, that can do the same essential job using something else in place of oxygen. One of the most widespread alternatives is sulfate, which is a simple compound of sulfur and oxygen, and which happens to be extremely abundant in seawater. It is one of the standard ingredients of the ocean, present everywhere, in every liter of it, all the time. Bacteria that use this route are called sulfate reducers, and they are common in exactly the places you would expect. Anywhere organic material is breaking down without access to oxygen. The mud of an estuary, the bottom of a stagnant pond, waterlogged soil, the black layer a few centimeters down in the sand of a tidal flat, which anyone who has ever dug on a beach at low tide has probably uncovered without thinking much about it. And they leave a signature that is impossible to mistake, because the byproduct of what they do is hydrogen sulphide. That is the smell. The faint, eggy note that comes off disturbed estuary mud, or off a marsh at low water on a warm evening, or out of a drain that has stood too long. It is one of the most recognizable smells in the natural world, and almost everyone has met it. If you have ever walked out across a mudflat and felt the crust give way under your boot and caught that sharp mineral whiff coming up, you have stood directly on top of the same process that is about to run inside a whale skeleton 4,000 meters down for the next several decades. The beginning of it goes like this. Once the soft tissue is largely gone and the bones are exposed, seawater begins to work into the porous structure of the skeleton. Bacteria go with it. Inside the bone, in the small spaces of the matrix and around the fat stored there, oxygen is used up almost immediately by the first arrivals and is not replaced because water does not circulate freely through bone. What is left is an interior that is wet, rich in fat, entirely without oxygen, and full of dissolved sulfate from the seawater that carried the bacteria in. For a sulfate-reducing bacterium, this is close to ideal. So they set to work on the lipids, slowly, in the cold, using sulfate in place of oxygen, and hydrogen sulfide accumulates inside the bone and then begins to diffuse out of it, seeping from every pore and crack of the skeleton into the water and the sediment around it. And this is where the whale fall becomes something other than a large meal, because hydrogen sulfide is itself a fuel. There is a second group of bacteria, entirely separate, that can do the opposite trick. They take hydrogen sulfide, combine it with oxygen from the surrounding seawater, and use the energy released by that reaction to build sugars out of dissolved carbon dioxide, which is to say, they make food out of chemistry, in complete darkness, with no sunlight involved at any stage. The process is called chemosynthesis, and it is the exact structural counterpart of photosynthesis. A plant uses light energy to build sugar from carbon dioxide and water. These bacteria use chemical energy to build sugar from carbon dioxide and hydrogen sulfide. The product is the same, and the purpose is the same, and only the power source is different. For most of the history of biology, nobody thought whole ecosystems could be built on this. Then, in 1977, a submersible working on the Galapagos Rift found hydrothermal vents, and around them, in water that no sunlight had touched in the entire history of the planet, an abundance of large animals that had no business being there, tube worms 2 meters long, clams the size of dinner plates, crabs and shrimp in crowds, all of it running on hydrogen sulfide coming out of the vents, converted by bacteria, and passed up into animals that had, in several cases, evolved to house those bacteria inside their own bodies rather than bothering to eat them. The story of that dive deserves telling properly because it is one of the few occasions in modern science when people went down expecting one thing and came back with something nobody had thought of. The expedition was a geological one. The interest was in the ridge itself, in the way new seafloor is made where two plates pull apart, and in the possibility that seawater was circulating through the hot rock and coming back out somewhere. The instruments had already found small anomalies of warm water in the area. The team wanted to see where they were coming from. There was no biologist on the ship for that first dive, because nobody had any reason to think one would be needed. What the pilots saw, when Alvin came down over the ridge and the lights went on, was a stretch of dark volcanic rock with shimmering water rising off it, and around the shimmer, an abundance of animals that had no place being there at that depth. clams the size of a hand, in beds, crabs, pale and unbothered, mussels, and standing up from the rock in dense clusters, white tubes over a meter tall with scarlet plumes emerging from the ends of them, swaying. The transcripts from that dive are worth reading. There is a good deal of confusion and a certain amount of laughing, and somebody says that they are not supposed to be finding this. They collected what they could and brought it up, and then discovered that a geological expedition does not carry the chemicals required to preserve biological specimens properly. What they had was a supply of Russian vodka, and so a number of the first hydrothermal vent animals ever collected went into the jars in that, which is the sort of detail that gets repeated for 50 years because it deserves to be. The tube worms, when they were finally examined by people qualified to examine them, produced the same puzzle that Osedax would produce 25 years later. They had no mouth and no gut and no digestive system of any kind. They were more than a meter long. They were growing quickly, and there was no visible mechanism by which anything was getting into them. The answer came from a graduate student named Colleen Kavanagh, who proposed and then demonstrated that the interior of the worm is packed with bacteria held in a specialized organ that occupies most of the body, and that those bacteria are doing chemosynthesis on hydrogen sulphide supplied by the worm's own blood. The scarlet plume is the intake. It absorbs sulphide and oxygen from the water and carries both down to the bacteria in a hemoglobin, unlike anything else in the animal world, one that can transport the two together without the one destroying the other. So the worm is not really an animal that eats. It is an animal that farms internally and has dispensed with the whole apparatus of feeding because it no longer needs it, which is precisely the arrangement that would be found later on whalebone, arrived at independently in a different family of worms, in a different setting, on a different chemical supply. Two animals, unrelated except distantly, both of them abandoning the digestive system entirely and handing the job to bacteria. When the same solution turns up twice in unconnected lineages, it usually means the solution is a good one. That discovery was one of the great reorganizations in 20th century science, and the whale fall connects to it directly because a whale skeleton generating hydrogen sulphide from the fat inside its own bones is producing precisely the same currency as a hydrothermal vent, less of it and more slowly, and in a form that runs out eventually. But the same currency, in the same coin, spendable by the same kinds of animals, which is exactly what shows up. The first sign, visually, is the mats. Bacteria that oxidize sulphide often grow in dense visible films, and on a whale skeleton in this condition they spread across the bone in sheets of white and pale yellow, sometimes filamentous, sometimes smooth, following the contours and gathering thickest where the sulphide is seeping out fastest. On video from a submersible it looks like frost, like a fall of thin snow that has settled unevenly on the ribs and along the spine and drifted into the hollows of the skull, standing out very bright in the lights against the gray of the sediment and the dark beyond. Some of these bacteria form long filaments that sway slightly in the current. Some accumulate small internal granules of sulfur that make them faintly luminous under a bright beam. Then the animals that live off them, mussels, arrive, and they are close relatives of the mussels that grow at hydrothermal vents. Small ones, mostly an inch or two, settling in clusters in the crevices between vertebrae and along the seams of the skull, and their gills are packed with symbiotic bacteria that do the chemosynthesis on their behalf. The mussel provides a safe housing, a steady supply of both sulphide from the bone and oxygen from the water, and in return it is fed from the inside. Several genera turn up at whale falls around the world, and finding them there was one of the earliest hints that these sites were something more interesting than a large meal. Clams settle into the enriched sediment beneath and beside the bones, some of them from families that are otherwise known almost exclusively from vents and cold seeps, and they run the same arrangement. Bacteria in the gills, chemistry instead of grazing. Limpets fasten themselves onto the bone surface and graze the bacterial mats directly. Small crustaceans work along the seams. Certain snails specialize in the mats. Around and among all of them, polychaete worms in a variety unusual even for polychaetes, some of them living nowhere else that anyone has found, and the whole assemblage settles in for the long stay. This is the sulfophilic stage, and the word simply means sulphide-loving, which is a plain description of the whole community. It is the longest of the three by an enormous margin. The mobile scavengers work for months to a couple of years. The enrichment opportunists have their spike and then subside. The sulfophilic stage, on a large whale, in cold, deep water, is currently thought to run for decades. How many decades is one of the genuinely open questions in the field, and the honest answer is that nobody knows with any precision, because nobody has watched one all the way through. The estimates come from measuring how fast lipid is disappearing from bones at known sites, and extrapolating. And the extrapolations for the largest whales stretch out to 50 years, and in some calculations rather more. That is a long time to sit at 4,000 meters in the dark, quietly turning fat into sulphide, feeding several generations of mussels. It is, incidentally, longer than most of the people who study these sites will have careers. And it means that a whale fall is not really an event, it is an institution. It arrives, it goes through a rapid and crowded few years, and then it settles into a long, slow, stable middle age, during which almost nothing changes from one decade to the next. If you visited the same skeleton in 1990 and again in 2010, you would find it recognizably the same place, a little more collapsed, the bones a little more porous, the mats in slightly different positions, the mussels perhaps in their third or fourth generation, all of it running on the same fat that the whale laid down while it was alive and swimming somewhere in the sunlit ocean, 60 years earlier, eating krill. There is something quietly satisfying about that arithmetic, and it is worth holding on to as we go further down. The energy in those mats and mussels came from the sun. It was captured by microscopic plants at the surface of the sea, eaten by krill, eaten by the whale, stored in the whale's bones, carried down 4,000 meters, and then released, slowly, over half a century, in complete darkness, by bacteria that have never encountered light and never will. Sunlight, deposited. Withdrawn 50 years later, in the dark, in another form, and there is one animal that gets into the bank vault more directly than anything else, and it is not like anything you have met so far tonight. In February of 2002, a remotely operated vehicle belonging to the Monterey Bay Aquarium Research Institute was working in the canyon that runs out from the coast of Central California at a depth of a little under 3,000 meters. Monterey Canyon is one of the best studied pieces of deep seafloor anywhere in the world, partly because it is genuinely interesting and partly because it happens to lie a short boat ride from a very good laboratory, which is the sort of accident that shapes whole fields of science. The vehicle was doing routine work. In the course of it, the pilots came across a whale skeleton lying on the sediment, the remains of a gray whale, largely stripped, ribs and vertebrae scattered across the ooze in a rough approximation of the shape the animal used to have. That in itself was a good find and worth stopping for. But when the lights came up close on the bones, the researchers watching the video feed on the ship above saw something none of them recognized. The bones were covered in red. Not stained red, but covered. In a dense growth of soft crimson plumes standing up off the surface of the vertebrae and the ribs, each one only a few centimeters tall, packed close together and moving gently in the current, so that the whole skeleton looked upholstered. The comparison people reached for at the time was a shag carpet, and the photographs bear it out. A pale bone, and on top of it a deep red pile, waving very slightly. Nobody knew what it was. They collected samples, brought them up, and started looking properly. And the answer took some time to assemble because the animal did not fit tidily into anything. It was a worm. That much was clear. A polychaete. From the annelid line, the red plumes were the visible part, and their color came from hemoglobin, the same molecule that makes blood red in you and in every other vertebrate, used here for the same purpose of picking up oxygen out of the surrounding water. Below the plumes, a soft trunk wrapped in a clear tube of mucus. And below that, where in almost any other animal there would be some sort of a body, there was a root system. That is the word the researchers used, because that is what it looks like. A green branching structure, growing not into sediment but into the bone itself, ramifying through the mineral matrix, spreading out into the interior of the vertebra like the roots of a small tree spreading through soil. Some of it thin and thread-like, some of it swollen into lobes, working its way inward into the fat store from a hold on the outside surface. Then they looked for the digestive system, and there was not one. There was no mouth, and no gut, and nothing resembling a digestive tract anywhere in the animal. Nowhere for food to go in, nowhere for anything to be broken down, nowhere for waste to come out. An animal several centimeters long, in visibly excellent health, reproducing enthusiastically, entirely lacking the apparatus that we usually consider the minimum requirement for being an animal at all. The genus was named Osedax, from the Latin for bone and a word meaning devouring. And the first two species described were given names for the red of the plume and in honor of a colleague. The description was published in 2004, and it made news well beyond the field, partly because of the strangeness of the thing, and partly because of the way the pieces eventually fitted together. The way it works, as far as anyone currently understands it, goes something like this. The root tissue secretes acid. The cells of the root surface are equipped with molecular pumps that push protons outward, lowering the pH right at the interface between the worm and bone dissolves in acid. This is not an exotic process, incidentally. It is essentially the same mechanism your own body uses to remodel your skeleton, which is happening in you continuously. Specialized cells called osteoclasts sit on a patch of bone, seal the edges, acidify the space beneath, and dissolve the mineral away so that it can be rebuilt elsewhere. Osedax appears to have arrived at a comparable solution independently, and it uses it not to remodel but to tunnel, which gets the worm into the bone. But the worm still cannot eat what it finds there, having nothing to eat with. So the digestion is subcontracted. Inside the root tissue, in enormous numbers, live symbiotic bacteria. They are heterotrophic, meaning they consume organic material rather than making it, and they break down what the acid releases from the bone, the collagen and the lipids, and the worm absorbs the products directly across its tissues. It is a partnership of a kind that turns out to be common in the deep sea once you start looking, though this particular arrangement is unusual, even by those standards. The worm provides access and shelter and oxygen. The bacteria provide the chemistry. Neither could manage the bone alone. And then there are the males. When the first specimens were examined, every single animal collected was female. Everyone. Hundreds of them, all mature, many carrying eggs, and no males anywhere in the samples. This was awkward, since the eggs were clearly being fertilized. The males were found eventually, inside the tubes of the females, and they are microscopic, something in the region of 1/10 of a millimeter. Dozens of them in a single female's tube, in some species over 100, packed into the gelatinous sheath around her trunk like grains in a pod. They have no roots, no plumes, no bacteria, and essentially no body beyond a sac of sperm and a remnant of the yolk they were born with, which they never finish using. They are, structurally, larvae that stopped developing and became reproductive instead. What determines which one an individual becomes appears to be nothing more than where it happens to land. A larva that settles on bare whalebone develops into a female, grows roots, acquires bacteria, and gets on with it. A larva that settles on a female already in place becomes a male, stays tiny, and stays where it landed. It is one of the more efficient solutions to the problem of finding a mate in an enormous dark ocean where the nearest suitable habitat may be 100 kilometers away and may not exist at all. Do not search. Arrive at the same address and let the arrangement sort itself out. The other half of that problem is getting to the bone in the first place. And here the strategy is simple volume. A mature female Osedax produces eggs more or less continuously in very large numbers and releases them into the water above the skeleton. The larvae that hatch are tiny and they can swim a little, but mostly they drift, carried by whatever slow current is passing. And they can apparently remain viable in the water column for weeks, which, at the speeds involved down there, might carry one some tens of kilometers from where it started. The overwhelming majority will never encounter a bone. There is no reason they should. The seafloor is enormous, and whale skeletons are extremely rare, and a larva drifting through the dark at 4,000 meters is playing odds that would be considered unreasonable in any other context. So the answer is to release so many that the odds stop mattering. It is the same solution used by oysters, by corals, by most of the sessile life in the sea, and it works for exactly the same reason. If 100,000 larvae go out and 2 find a whale, the species continues. And when they do find one, they are quick about it. In experiments where clean bones have been placed on the deep sea floor and revisited, Osedax has been found established on them within a couple of months. Roots already growing inward, some individuals already reproductive. For an animal in near-freezing water at great depth, that is a remarkable turn of speed, and it suggests that at any given moment the deep ocean contains an enormous drifting population of these larvae, spread thin through the water, waiting for something to land on, which means that when our whale settled onto the sediment in the first hours of tonight's story, before the amphipods arrived and long before anything had touched the bone, the worms that would eventually cover it were already in the water above, drifting past in the dark, in numbers nobody has ever counted, most of them destined to go by without noticing. Since 2002, Osedax has been found almost everywhere anyone has thought to look for it. Dozens of species are now known or suspected, from the Pacific and the Atlantic and the Southern Ocean and the seas around Japan. One species was found off the coast of Sweden at a depth of little more than 100 meters, on a minke whale skeleton in the North Sea, which was a considerable surprise since the genus had been assumed to be an animal of the deep. They are not fussy about the source of the bone either. Experiments in which cow bones, or fish bones, or the bones of seabirds were placed on the seafloor have all been colonized. Osedax is not a whale specialist. It is a bone specialist, and whales simply happen to be the largest quantity of bone the ocean ever produces. There is also a question, still being worked on, about how long Osedax has been doing this, and the evidence for it comes from an unexpected direction. Fossil whale bones sometimes carry distinctive borings, cavities of a particular shape that match the root systems of modern Osedax quite closely. Such borings have been reported in fossil marine bones going back tens of millions of years, well beyond the age of the modern species, which suggests that this way of life is ancient and that bone-eating worms were already at work on whale skeletons long before anything resembling a human being existed. And that raises a rather good problem, which some researchers have taken seriously. If Osedax has been dissolving whale bones on the seafloor for tens of millions of years, and doing it as efficiently as it does now, then a certain number of whale skeletons that might otherwise have fossilized were quietly taken apart instead. Our record of whale evolution might be patchier than it would otherwise be, not because the whales were rare, but because something was eating the evidence. There is a further consequence, closer to home, which is what Osedax does to the timetable of the whale fall itself. A skeleton heavily colonized by these worms is being opened up from every direction at once. Every root system is a channel into the interior, a passage for seawater and for bacteria, a breach in the sealed tank. Bone that might have held its fat for decades can be reduced to something soft and porous in a much shorter time, and at some sites the bones have been described as crumbling under the manipulator arm of a submersible after only a few years. So there is an active discussion in the field about whether Osedax substantially shortens the life of a whale fall, and whether the 50-year estimates hold everywhere, or only in places where the worms are, for whatever reason, thin on the ground. It is not settled. Different sites give different answers, and the number of natural whale falls that anyone has been able to follow over time is small enough that general rules are hard to draw. Which brings us to the thing that shapes this entire subject, and which is easy to miss if you only read the conclusions. Almost nobody has ever seen this happen. The first whale fall that anyone studied properly was found in 1987, which is astonishingly recent. There were people alive and working then who had already spent whole careers in marine biology, and the entire subject we have been discussing tonight did not yet exist as a subject. There had been hints. Over the previous century, deep-sea dredges and trawls had occasionally come up with whale bones tangled in the net, and sometimes those bones had shells attached to them, small bivalves of a kind that did not seem to belong on a bone. Museum drawers here and there held such specimens, cataloged and shelved and not much thought about. Nobody assembled them into an idea. There was no reason to. A bone with a clam on it is a curiosity, not a hypothesis. Then a team led by an American oceanographer named Craig Smith was working in the Santa Catalina Basin off Southern California at around 1,200 meters on a rather different question. They were interested in how the deep-sea floor responds to small parcels of food arriving from above, and they were surveying the bottom with a towed camera system, taking photographs on a transect, which is exactly as painstaking as it sounds. In the developed images, there was a whale skeleton. They went back in Alvin, the American research submersible, which by then had already had a long and distinguished career, including the dives on the Galapagos vents 10 years earlier. They found the bones lying on the sediment, the remains of a large baleen whale, well past the stage of having any flesh left. And when they looked closely, they found the bones carrying dense growths of bacterial mat and clusters of mussels and clams in the crevices, and a whole community of animals that had no business being on a dead whale in the middle of an otherwise ordinary basin floor. Several of the species were ones known from hydrothermal vents. The paper that came out of it, a couple of years later, is the beginning of the field. It set out the essential proposition, which is that a whale skeleton on the seafloor becomes a chemosynthetic habitat, running on sulphide, of the same general type as a vent or a cold seep, and that it can do so for a very long time. Everything since has been built on that, and almost all of it has been built the hard way. Because there is a fundamental problem with studying whale falls, and it is a problem of arithmetic. The abyssal seafloor covers more of this planet than every continent combined. A whale skeleton is perhaps 20 meters long. Finding one on purpose, in the dark, at 4,000 meters, without knowing in advance that it is there, is a proposition of a kind that does not really have an equivalent on land. It is not looking for a needle in a haystack. It is looking for a needle in a country. There have been attempts to estimate how many are down there at any given moment, and the numbers that come out are large. If you take the populations of the great whales, and their life expectancies, and therefore the rate at which they must be dying, and then estimate how long a carcass persists on the seafloor, you arrive at a figure of hundreds of thousands of whale falls in some stage of the process at any one time, across all the world's oceans. Some estimates for the largest species alone run to something like 2/3 of a million. Along the migration routes of certain whales, the spacing may be as close as a few kilometers, which for a deep-sea animal trying to find one is practically a suburb. And yet the number that anyone has actually located and studied is measured in dozens. So the field has resorted to a workaround, and it is a wonderfully practical one. If natural whale falls are too hard to find, make some. Whales strand on beaches with some regularity, and the disposal of a large stranded carcass is a genuine logistical problem for whoever owns the beach. Beginning in the 1990s, Smith and his colleagues arranged for a number of these animals to be towed out to sea, weighted with scrap iron and old railway wheels, and sunk deliberately at chosen sites off the coast of California, where their positions were recorded precisely, and they could be visited again and again over years with a submersible or a remotely operated vehicle. That is where a great deal of the detail comes from. The rates of tissue removal, the succession of the stages, the sediment chemistry, the timing of the mussel arrivals, the behavior of Osedax. It is careful, patient, long-term work, funded across multiple grant cycles, carried out by researchers who in some cases visited the same skeleton for 20 years and watched it slowly change. But an implanted carcass is not quite the same as a natural one. It arrives all at once, having been intact at the surface. Its position is known. Nobody was watching the ones that fell on their own, and that is the honest state of things. The picture we have of the whale fall is assembled from a modest number of implanted carcasses studied thoroughly, a smaller number of natural ones found by luck and visited at unknown ages, some laboratory work, and a good deal of careful inference. Nobody has ever followed a single natural whale fall through the whole of its life, from the death at the surface and the sinking, through the scavengers and the opportunists and the long sulfophilic decades, to the end. The time scale alone makes it difficult. A 50-year study is longer than most funding structures, most equipment, and a fair number of the researchers. There is also a shadow over the numbers that is worth mentioning plainly, because it is part of the science rather than a digression from it. The great whales were hunted, intensively, through the 19th and 20th centuries, and their populations were reduced very sharply indeed before the hunting largely stopped. Fewer whales alive means fewer whales dying, and fewer whales dying means fewer of these habitats forming on the seafloor. Some researchers have suggested that the amount of whale fall habitat in the world's oceans may have dropped substantially over that period, and that specialist species which depended on it may have declined, or in some cases disappeared, without anyone ever knowing they were there. It is impossible to test directly. It is also difficult to dismiss. The more cheerful corollary is that some whale populations have recovered considerably since, and are continuing to, and the seafloor will have registered that too, quietly, over decades, in a way nobody was in a position to observe, all of which is background for what a team of researchers found when they went looking somewhere nobody had properly looked before, because the map has a great deal of blank on it still. Depending on how you measure it and how good you require the data to be, something like a quarter of the world's seafloor has been surveyed at any decent resolution. The rest is known only in the broad way that satellite gravity measurements allow, which gives you the shape of the big features and tells you essentially nothing about what is lying on them. There are whole basins and trenches and fracture zones where no human eye and no camera has ever been. One of them runs east to west across the floor of the southeastern Indian Ocean, between Australia and Antarctica, for about 1,200 kilometers. The Diamantina Zone is a long scar on the floor of the southeastern Indian Ocean, a rift valley and fracture system running between Australia and Antarctica. It exists because those two continents used to be joined and are not anymore. The separation began something like 50 million years ago, and the Diamantina Zone is part of the seam where the tearing happened. a stretched and broken stretch of ocean floor with valleys in it that go down a long way. At its deepest, it reaches a little over 7,000 meters. That puts the bottom of it into the Hadal Zone, which is the name given to everything below 6,000 meters, the deepest tenth of the ocean, found almost entirely in trenches and rifts of this kind. The Hadal Zone accounts for a very small fraction of the seafloor by area and includes essentially all of the deepest places on Earth. And it is, for obvious reasons of pressure and access, the least visited environment on the planet. In 2023, a team from the Institute of Deep Sea Science and Engineering, part of the Chinese Academy of Sciences, took a research vessel out to the Diamantina Zone with a crewed submersible aboard. The submersible is called Fendusha, a name usually translated as striver, and it is one of a small number of vehicles in the world capable of carrying people to full ocean depth. It had already been to the bottom of the Challenger Deep in the Mariana Trench, which is the deepest known point in any ocean, 3 years earlier. The expedition had a broad set of objectives, as these expeditions usually do, with geologists and geophysicists and biologists all aboard and all wanting different things. One of the stated aims was to look for fluid activity on the Hadal seafloor, seeps and vents and the chemistry that comes with them. On one of the dives, they found a whale fall. That alone would have been notable at that depth, but they kept diving, 32 times in all, working along the zone, and what emerged over those weeks was not a whale fall. It was a landscape of them. The findings were published in the journal Nature in June of 2026, and the paper describes something that had no precedent in the literature. Across roughly 1,200 kilometers of seafloor, at depths ranging from 4,616 meters down to 7,001 meters, the team recorded 5 active whale fall communities and 476 fossil sites, bones and skeletons and skulls, some of them clearly ancient, lying across the floor of the rift in numbers that nobody had anticipated and nothing in the previous record would have suggested. The researchers called it a whale necropolis, which is a heavier word than the place probably deserves. What the video shows is not somber. It is a pale seafloor with old bones on it, some half buried, some sitting proud of the sediment, some carrying growths of pink and white, brittle stars folded over them, small worms standing up off the surface. It looks less like a burial ground than like an old field where something has been settling for a very long time and nobody has cleared it. Several things about it were new. The first was the depth. Before this, essentially every whale fall known to science had been found at less than 4,000 meters, and the deepest active one anywhere in the record was at just over 4,200 meters in the southwest Atlantic. Nothing living on a whale carcass had ever been reported from Hadal depths at all. There were reasonable arguments for why not. Pressure, temperature, the difficulty of the chemistry, the sheer improbability of a carcass ending up in the narrow ribbon of a trench rather than on the broad plain either side of it. One of the active communities in the Diamantina Zone lies below 6,000 meters, which makes it the first active whale fall ever recorded in the Hadal Zone and moves the boundary of the whole phenomenon down by a considerable distance. It is worth understanding what that means, because the Hadal Zone is genuinely a different proposition from the abyss above it. The name comes from Hades, and it was chosen more for the depth than for any quality of the place, which is in practice rather calm. What defines it is pressure. At 6,000 meters, the water above is pressing down at roughly 600 times the pressure at the surface. At 7,000, closer to 700. In everyday terms, that is something like the weight of a small car resting on every square centimeter of everything, continuously, in every direction at once. Animals cope with this better than intuition suggests, because a body made of water and solid tissue does not compress much, and therefore does not experience pressure as a crushing force in the way we imagine. The real difficulty is molecular. At those pressures, proteins begin to change shape, and a protein that has changed shape usually stops working. Enzymes fold incorrectly, and cell membranes stiffen, and the machinery of a cell is finely balanced, and pressure of that magnitude pushes on the balance. The solution that deep-sea animals have arrived at is chemical, and it is a rather satisfying one. Their tissues accumulate a small stabilizing compound called trimethylamine oxide, which sits alongside the proteins and helps them hold their proper shape under pressure. The compound has an incidental fame at the surface, because when a fish dies and bacteria start breaking that compound down, the product is what we recognize as the smell of fish. So the characteristic smell of a fish market is, in a roundabout way, the smell of the molecule that lets deep-sea animals exist at all. Measurements have found that the concentration of it in fish tissue rises steadily with the depth the fish lives at, which is a neat and testable relationship. And if you extend that line downward, there comes a depth at which the required concentration would be so high that the internal chemistry of the animal would stop working for a different reason. The predicted limit falls somewhere in the region of 8,200 meters, which is interesting because the deepest fish anyone has ever filmed was recorded at just over 8,300 meters in a trench off Japan, a small pale snailfish moving unhurriedly across the sediment. The prediction and the observation landed within a few tens of meters of each other, which for this kind of biology is an unusually good result. Snailfish are the characteristic hodlfish, and they are appealing animals. Pale, small, without scales, with soft gelatinous bodies, and a slightly startled expression, drifting along the bottom of the deepest trenches on Earth, in the most physically extreme habitat available to a vertebrate, appearing entirely unbothered. They feed largely on amphipods, which swarm at Hadal depths in enormous numbers. And that is the other thing about trenches and rifts, which matters directly to what was found in the Diamantina Zone. A trench is a funnel. Material that lands anywhere on the slopes above it tends, over time, to end up in the bottom of it, moved along by slumps and currents and gravity. So the deepest parts of the Hadal Zone are often better supplied with organic material than the flat abyssal plains around them, which is the reverse of what you would expect, and a large part of why they support as much life as they do. Put a whale carcass anywhere near a rift like that, and the rift is where it is likely to end up. The second was the density. In parts of the zone, the researchers counted remains at something like 760 individuals for every square kilometer of seafloor, which is a concentration far above anything documented anywhere else. Extrapolating across the whole system, the team's estimate is that there may be more than 10 million whale remains lying in that one zone. 10 million. In one fracture on the floor of one ocean. The third was the age. Isotopic dating of the fossil material indicates that whale falls have been arriving in the Diamantina Zone for at least 5.3 million years, continuously, one animal after another, across a span of time that reaches back well before any recognizable human being existed anywhere on the planet. The oldest skull they recovered dates to around that figure. The accumulation has simply been going on, quietly, at the bottom of that rift, through ice ages and continental drift, and the entire rise of everything we would consider modern. And the fourth was what the bones turned out to be. A large proportion of the fossil material comes from beaked whales, which is a group worth knowing about, because they are the most elusive large animals on the planet. There are more than 20 species, and several of them have never been reliably seen alive. They are deep divers, extraordinarily so. One species holds the record for the longest recorded dive by any mammal, several hours on a single breath, at depths that would have seemed impossible for an air-breathing animal before the measurements came in. They spend most of their lives far below the surface. They surface briefly and inconspicuously, and they live in the open ocean far from any coast. Much of what we know about several species comes from bones that washed ashore or turned up in a net, and here they were, in quantity. Hundreds of them, including species that still exist and species that do not. Extinct beaked whales and living beaked whales, lying on the same seafloor, sorted by nothing but time. Getting any of it back to the surface is its own quiet undertaking. A crude submersible at 7,000 meters has one hydraulic arm and a limited number of hours, and the arm is precise but not delicate in the way a hand is. So recovering a fossil skull from soft sediment is a slow business of positioning and easing and lifting, watched through a small acrylic port by somebody lying on their front in the cold. There is also a device called a slurp sampler, which is exactly what the name suggests. A suction tube for picking up small animals without damaging them, and it is how most of the living material from sites like this comes home. Across the whole set of dives, the team recovered somewhere in the region of 40 fossil specimens, along with samples of the animals living on the active sites. That is a modest haul for 32 dives, and it is a good illustration of how this work actually goes. Weeks at sea, an enormous quantity of video, and a few boxes of bone. The bones then went to laboratories in 3 countries because the study was a collaboration, with the Chinese institute that ran the expedition working alongside colleagues in Italy and in New Zealand. Identifying a beaked whale from a fossil skull is specialist work, and there are not many people in the world who do it. Dating one is a different specialism again, and it relies on measuring the slow radioactive decay of elements incorporated into the mineral while the animal was alive, and afterwards, which is how a figure like 5.3 million years is arrived at. with error bars attached to it and a good deal of care taken over the assumptions. There is something quietly companionable about that whole process. A whale dies in the open ocean in the Pliocene, sinks into a rift on the seafloor, and lies there while the continents move a little, and the ice comes and goes several times, and every species of hominin that has ever existed appears and, mostly, disappears again. And then a hydraulic arm reaches down and lifts it and puts it in a box, which is the part of the finding that changes the subject rather than just extending it. Because if whale bones can persist on the deep seafloor for millions of years in a place like this, then the deep seafloor is not only a habitat, it is an archive. It is worth taking a moment over what that means. The fossil record of whales on land is, by the nature of things, a coastal record. Fossils form where sediment accumulates and where the rock later ends up somewhere a person can reach it. And that means shallow seas, ancient shorelines, uplifted marine sediments now sitting in a desert or a road cutting somewhere. The whales that lived and died in the open ocean, far from any coast, mostly left no record at all that anyone could get at. The Diamantina Zone is the open ocean. It is about as far from a coastline as it is possible to be, and it has been quietly collecting the skeletons of deep-diving whales for 5 million years and keeping them, more or less in order, layered by time, in a place where the water is cold and still, and the sediment accumulates so slowly that things lie exposed for an extraordinarily long while before they are buried. The researchers who found it have suggested it may hold a record of cetacean evolution, and particularly of the beaked whales, that exist nowhere else and could not exist anywhere else. A history of the deep-diving whales, written by the deep-diving whales, filed on the floor of the ocean they dived into. They also suggested something else, which takes us back to the vents. Hydrothermal vents have a problem, and it is the problem of every island. A vent field forms where seawater sinks into cracks in the seafloor near a spreading ridge, is heated by the rock beneath, dissolves minerals out of it, and comes back up through a chimney. The animals that live around it are dependent on that flow, and the flow is not permanent. Plumbing shifts, and cracks seal, and eventually an eruption buries the whole thing under new lava. Vent fields have lifespans, and while the estimates vary a great deal with the setting, many of them are thought to persist for decades or centuries rather than for geological ages. So every population of vent animals is living somewhere temporary, and the nearest other suitable place may be tens or hundreds or thousands of kilometers away along the ridge, or across an entire ocean basin. The habitat is scattered, short-lived, and separated by enormous distances of ordinary seafloor, where none of these animals can live at all. And yet they are there, everywhere, on ridges across every ocean, and closely related species turn up at vent fields that are very far apart indeed. So the animals are getting from one place to another somehow. Part of the answer is larvae. Many deep-sea invertebrates release larvae that can drift in the water column for weeks, some of them carrying a yolk supply that lets them travel without feeding, riding whatever current is going, and settling if they happen to encounter somewhere suitable. Most do not. The arithmetic of larval dispersal is unforgiving, and the overwhelming majority of larvae released anywhere in the ocean settle nowhere and are never heard of again. But there are a great many of them, and enough succeed to keep the system running. The other part of the answer, or at least a proposed part, is whale falls. The idea was put forward not long after that first Santa Catalina skeleton, and it follows fairly naturally from what was on it. If a whale skeleton produces sulphide, and vent animals live on sulphide, and there are hundreds of thousands of whale skeletons scattered across the world's seafloor at any moment, then the ocean floor is not a barren gulf between vent fields. It is dotted with small, temporary, chemically suitable places to stop. Stepping stones, in other words. A chain of modest habitats, each one lasting decades, each one within larval reach of the next, allowing lineages to move gradually across distances that no single larva could ever cross in one go. It is an attractive hypothesis, and it has been argued over for more than 30 years, which is generally the sign of a good one. The evidence for it is partly in the species lists, because certain groups genuinely do turn up in all three settings. Mussels of a particular family are found at vents, at cold seeps where methane and sulphide leak from the sediment, at sunken wood, and on whale bones. Clams of the vesicomyid family, likewise, various polychaetes and limpets and snails. There is real overlap, and it is not the sort of overlap that happens by accident. The evidence against is that the overlap is not as neat as the hypothesis would like. When researchers built family trees from genetic data, tracing which lineages are most closely related to which, The pattern that came out was more complicated than a simple ladder from shallow organic falls to deep vents. Some groups look as though they did move that way. Others look as though they did not, or did it in a different order, or several times independently. And a good many whale fall species turn out to be found on whale falls and nowhere else, which suggests that this habitat is not only a staging post but a home in its own right, with its own specialists that never go anywhere near a vent. The current position, as far as there is one, is that whale falls probably do serve as dispersal habitat for some chemosynthetic lineages some of the time, and that they are also a distinct habitat with a fauna of their own, and that the relationship between the two roles differs between groups and between oceans, which is a less tidy answer than the original idea, and almost certainly a more accurate one. What the Diamantina finding adds is a matter of scale and of geography, because if a whale fall is a stepping stone, then the spacing of the stones matters enormously. A chain with a gap of 2,000 kilometers in it is not a chain, and most estimates of whale fall spacing, before this, were based on whale populations and ocean areas, and produced figures on the order of tens of kilometers in the busiest places, and a great deal more in the empty ones. The Diamantina Zone is not spaced in tens of kilometers. It is a continuous accumulation running for 1,200 kilometers along a rift on the floor of the southeastern Indian Ocean, with remains dense enough in places to be counted in the hundreds per square kilometer. If that is what it looks like, then it is not a scatter of stepping stones. It is closer to a road. The team who described it used the phrase chemosynthetic life corridor and suggested that this stretch of the seafloor may function as a route across the southeastern Indian Ocean, along which chemosynthetic animals can move from one end to the other in a series of short hops over generations, over a very long time. Why the whales should end up there in such numbers is a fair question, and it does not have a confident answer yet. Beaked whales are deep divers and open ocean animals, and if a population of them lives and feeds over that region, then their remains would tend to arrive in the region. The topography may help. A rift valley is a valley, and things that fall near a valley have a tendency to end up in it, whether by falling directly, by sliding down the flanks, or by being moved gradually by the slow processes that shift sediment on a slope. And the conditions at the bottom, cold and still, and slow to bury anything, appear to be unusually good at preserving what arrives. It may also be that the Diamantina Zone is not unique at all, and merely the first place of its kind that anyone has looked at closely. That possibility is the one that most of the people writing about it seem to find interesting. There are fracture zones and rifts and trenches on the floor of every ocean, and almost none of them have been surveyed in this way. If this is what happens in one of them, it is entirely reasonable to wonder what is lying at the bottom of the others. Nobody knows. That is a real answer and not a dodge, and it is the state of most questions about the deep seafloor. Meanwhile, back at our own whale, the years are passing. Let us go back to the one we followed down, because it is still there, and it will be there for a long time yet. 5 years have gone by. The plain around it looks almost ordinary again. The great dark stain in the sediment has faded considerably. The population of small worms has fallen back towards something closer to normal, and the crowds of amphipods dispersed years ago to wherever it is that amphipods go between meals. The skeleton has come apart. Ribs lie scattered in a rough arc, sunk partway into the ooze, some of them pointing up at an angle where they came to rest. The vertebrae have separated and lie in a broken line, no longer really a spine, more like a sentence with the spaces taken out. The skull is off to one side, half buried, still the heaviest and most recognizable thing in the whole scene, and every surface of it is occupied. Bacterial mats in white and pale gold spread thin over the bone, muscles in clusters in the crevices, filtering nothing, being fed from within by the bacteria in their gills, limpets grazing the mats in slow curved paths. Osedax standing up off the bone in red plumes, in their hundreds, moving very slightly in a current you could barely detect if you were there. Brittle stars draped over the ribs, arms hooked around the bone, doing whatever it is that brittle stars are doing, which is a question that has never entirely been answered. Inside the bone, in the dark, in the wet interior spaces, the sulfate reducers are working through the fat at their own extremely unhurried pace, and hydrogen sulphide is diffusing outward continuously, as it has been for years, as it will for decades. Nothing about this scene will change appreciably between now and, say, the year after next. That is the thing about it that is hardest to hold in mind, coming from a world where everything is on a schedule. A whale fall in its long middle age is one of the most stable environments imaginable. The temperature does not vary, the light does not vary, because there is none. The current changes a little with the tides, in the very slow way that tides express themselves at 4,000 meters, and that is essentially the entire weather. There is no summer and no winter down there. There is no morning. The generations of mussels come and go on their own timetable, and the bone gets slowly more porous, and the whole assemblage runs on the fat of an animal that died before some of the people who might one day study it were born. It is also, and this is a strand worth following for a moment, a small piece of the planet's carbon accounting. A living whale is a very large quantity of carbon, walking around, or the oceanic equivalent. Roughly speaking, an animal's body is somewhere in the region of 10 to 15% carbon by weight, which for a 100-ton whale gives a figure of many tons, all of it originally taken out of the air as carbon dioxide, dissolved into the sea, fixed by microscopic plants at the surface, and emiced up the chain into krill and then into the whale. While the whale is alive, that carbon stays broadly within the surface system. It circulates. The whale breathes and eats and excretes, and the material moves around near the top of the ocean where it remains in contact with the atmosphere. When the whale sinks, a substantial part of that carbon leaves. It goes to the deep seafloor, and it stays there. Some of it consumed and respired by the animals that come to feed, some of it buried in the sediment, some of it locked into bone and released so slowly that it is effectively out of circulation for a human lifetime and beyond. Deep water does not mix with surface water quickly. On average, water at the bottom of the ocean will not see the sky again for several centuries, and in some basins considerably longer than that. Carbon delivered to the abyssal floor is carbon parked. Set against the total carbon cycle of a planet, the contribution of whale falls is modest, and it would be overstating things to present a few 100,000 carcasses as a major lever on the global system. The great mass of carbon that moves from the surface to the deep does so as marine snow, continuously, everywhere, in quantities that dwarf anything the whales contribute. But it is not nothing, and the mechanism is elegant. Whales spend decades assembling carbon into one very large body at the surface, and then deliver it, in a single parcel, to a depth it would otherwise mostly never have reached. There is a second half to this, which concerns what whales do while they are alive, and it has been studied with increasing interest over the last couple of decades. A whale feeding at depth and surfacing to breathe brings nutrients up with it, particularly iron and nitrogen, released in the water column near the surface where microscopic plants can use them. Iron in particular is scarce in much of the open ocean, and its scarcity limits how much can grow there. So a population of large whales fertilizes the water it lives in, and the growth that results feeds the krill that feed the whales. Researchers have called this the whale pump, and the broad conclusion is that a sea with whales in it is a more productive sea than the same water without them, which means that the hunting of the last 2 centuries did not simply remove the whales. It also, to a degree that is still being worked out, made the ocean itself less fertile than it had been. And it means that the recovery of whale populations, where it is happening, is doing more than restoring a species count. It is slowly restoring a process. More whales, more fertilization, more growth, more krill, more whales, and at the end of all of it, more of these strange, long-lived cities forming on the floor of the deep, none of which the whale knows anything about, of course. It simply lived, and swam, and ate, and eventually stopped, and the rest followed as it always has. The whale, incidentally, is not the only thing that falls. The deep sea gets deliveries of all kinds, and once you understand the whale fall, the others become much easier to see, because they all work on the same principle. Something concentrated and organic arrives in a place where food is scarce and evenly spread, and a specialized community assembles around it. The most studied after whale falls are wood falls, and they are more common than you might guess. Trees end up in rivers. Rivers carry them to the sea, and waterlogged wood eventually loses buoyancy and sinks. In some regions, particularly off the mouths of large tropical rivers, this happens on a considerable scale, and the deep seafloor beyond such a river mouth can carry a scattering of sunken trunks and branches. What lives on them is a community as distinctive in its way as a whale fall community. Wood-boring bivalves in the family that includes shipworms tunnel into the timber, assisted by symbiotic bacteria that break down cellulose, which is not a thing an animal can easily digest on its own. Their tunneling produces vast quantities of fine wood particles, which enrich the sediment around the log. And in the oxygen-free interior of a waterlogged trunk, sulfate reducers get to work exactly as they do inside whalebone, and produce exactly the same hydrogen sulphide, And around a sunken log you find bacterial mats and mussels, and the same general cast of chemosynthetic characters. A sunken tree, in other words, becomes a small whale fall. Or more accurately, a whale fall behaves very much like a sunken tree, since trees have presumably been arriving in the sea for a great deal longer. Kelp falls happen where forests of large seaweed grow near deep water, and great rafts of detached kelp sink into canyons and provide a briefer and less chemically dramatic version of the same thing. Falls of squid, of salps, of large fish, all occur, all get consumed, most of them too quickly to develop into anything more than a busy few days. There have been reports of shark falls, and one in particular that got some attention, in which a group of large fish were found feeding on a whale shark carcass on the seafloor in the Gulf of Mexico. There have been fish falls in enough number to show that even a modest carcass draws a crowd. There are the carcasses of seals, of turtles, of seabirds. There are, in certain unfortunate stretches of ocean, entire sunken loads of grain or timber from a lost ship, which for the animals below is simply a very large and slightly odd food fall. But nothing else in the ocean does what a whale does, because nothing else is that big and nothing else has that much fat inside its bones. That is the whole of the difference. A woodfall runs for years. A whale fall runs for decades, and it does so because a whale is not simply large, but built out of a material that the deep sea finds very difficult to open. Suppose for a while that you could go and see one. The vessels that do this work are small, and the part that holds people is smaller still. A crude deep submersible is essentially a metal sphere with instruments bolted to the outside of it, and the sphere is only about 2 meters across, which is the size of a modest bathroom. It has to be a sphere. At the depths involved, a sphere is the only shape that distributes the load evenly enough for the numbers to work, and every other consideration gives way to that one. You climb down through a hatch in the top and sit on a padded bench with your legs drawn up. There are 2 other people in there with you, usually, one of them flying the thing. There are 3 small viewports of very thick acrylic, one facing forward and one on either side, each about the size of a dinner plate at the inner surface and tapering outward. There is a smell of cold metal and electronics. The interior is lined with panels and cables and screens and the tidy chaos of a working vehicle. The hatch closes. The noise of the ship above stops being relevant. The descent takes hours, and it is, by every account of people who have done it, unexpectedly restful. There is nothing to steer. The vessel simply sinks, ballasted slightly heavy, at a steady rate of perhaps 30 or 40 meters a minute, and the pilots monitor systems and talk quietly and drink tea from flasks. There is not much to look at for the first part. Blue outside the ports, then dark blue, then a blue so deep it is only distinguishable from black because you have been watching it change. Somewhere below 200 meters, if you turn the interior lights off and give your eyes a few minutes, the outside starts to have things in it. Small blue-green flashes as the vessel disturbs animals in its path. Occasionally a long chain of light where a siphon of 4 has been brushed. Now and then something larger passes and lights up and is gone. This is the part that people who have done it talk about most, and they tend to run out of words for it, which is a good sign. By 1,000 meters it is black outside the ports, and there is nothing to see unless something makes light. By 2,000 meters it is cold inside the sphere. There is no heating to speak of, and outside the hull the water is a few degrees above freezing, and the metal conducts it in enthusiastically. Everyone puts on a hat and a fleece. Condensation forms on the inside of the hull and runs down in slow lines. This surprises people, but it is only the humidity of 3 breathing bodies meeting a cold wall. By 3,000 meters, the sinking has been going on long enough to have become normal, and there is a particular quality to the time that pilots describe well. You are not going anywhere in any visible sense. The instruments say the depth is increasing. Nothing outside confirms it. The hull creaks occasionally as it takes up the load, small, sharp sounds that are entirely expected and that everyone stops noticing after the first few dives. Then the sonar shows a bottom coming up, and the pilot slows the descent, and lights go on. The floor arrives in the lights as a pale surface, softer looking than you would expect, fine gray fawn ooze with a very slight texture to it, marked with tracks and small mounds and the odd shallow depression. It looks like fresh snow that has been walked on by something small. The vessel settles until it is hovering a meter or 2 above it, and the thrusters raise a faint haze that drifts off in the current. And then you go looking, and the looking takes a while, because a whale skeleton is 20 meters long, and the lights of a submersible reach perhaps 10 or 15 meters into that darkness, and beyond that there is nothing at all. The first sign is usually the sediment. Even years later, a whale fall site tends to have a slightly different color and texture around it, and a slightly different population of the small animals whose tracks mark the ooze. Then something at the edge of the lights, a pale curve, standing up out of the floor, a rib, and then the vessel moves forward and the rest of it comes into the light. There is no way to see the whole thing at once. That is the part that photographs and documentaries cannot honestly convey, because a photograph has edges and lighting and a whole frame, and down there you have a cone of light and everything else is dark. What you get is a series of pieces, assembled in your head over the 20 or 30 minutes it takes to work along the site. A rib, then another, then a gap of gray floor, then the long broken row of vertebrae, each one the size of a stool, sitting slightly askew, spaced by the distance the sediment has let them settle. Then, at the end, the skull. The skull of a large baleen whale on the seafloor is one of those objects that resets your sense of scale. It can be a quarter of the animal's length. It lies partly buried, jaw fallen away, the long bones of the rostrum stretching out ahead of it, and in the lights it is not white but a soft mottled gray and gold and rust, coated in growth, with pale mats gathered in the hollows. Everything is furred. That is the word people reach for. Nothing down there is a clean bone. The surfaces carry mats and films and small growths. The crevices carry muscles, and standing up off all of it in a dense, uneven pile are the red plumes of the bone-eating worms, moving very gently, all leaning slightly the same way where the current takes them, and it is silent. Not quite silent, in fairness. Inside the sphere there is the hum of the electronics and the whir of a thruster and the sound of the other two people breathing and speaking. But outside there is nothing at all, and the deep sea is one of the few places on this planet where that is genuinely true. There is no wind, because there is no air. There is no surf, no rain, no rustle of anything, no calls, because the animals down there are largely silent and widely spaced. Occasionally, the low moan of a distant whale comes through, since low-frequency sound travels extraordinarily well in the deep ocean and can cross a basin. Occasionally, there is a faint grinding from the earth itself. Otherwise, nothing. 4,000 meters of water pressing down, holding everything still, and a 20-meter skeleton lying in it, running quietly on stored sunlight, in the dark, with nobody watching for years at a stretch. Then the pilot checks the time, and the batteries, and the sample basket. And after a couple of hours of this, the vessel drops its ballast weights and starts back up, and the whole site slides out of the lights and back into darkness, and it will very likely be a long while before anyone visits again. The ascent is quicker than the descent, and everybody usually sleeps through most of it. What comes back up with the vessel is a small tray of the deep sea, and it arrives in a very particular condition. The sample basket on the front of a submersible holds insulated boxes, and the good ones are designed to keep their contents near the temperature they were collected at, because a deep-sea animal that spends 4 hours in water warming steadily towards the surface temperature does not usually survive the experience. Even so, the change in pressure alone is enough to finish a great many of them. Some groups cope surprisingly well. Others simply come apart. When the boxes are opened on deck, there is a smell, and everyone who has done this describes the same one. The eggy note of hydrogen sulphide, unmistakable, coming off a piece of whalebone that has been sitting on the seafloor for a decade or two. It is a small moment and a slightly startling one, because it is the exact smell of an estuary at low tide, arriving on a ship in the middle of the ocean, out of a box that has just come up from 4,000 meters. The bone goes into a cold room in seawater, and then people spend weeks going through it with fine forceps and a good lamp. What they find, mostly, is small. The animals that get photographed are the ones you can see from a meter away, and the ones that get counted are usually much smaller than that. A single fragment of whale vertebra, the size of a fist, can yield hundreds of individual animals from dozens of species, most of them a few millimeters long, most of them worms. Polychaetes dominate, in a variety that is difficult to convey without a microscope and a certain amount of patience. Some are simple pale threads. Some have paired bundles of bristles running the length of the body that catch the light like glass fibers. Some build tubes of mucus and sediment and live inside them permanently, projecting only a crown of tentacles into the water. Some are iridescent, for reasons nobody has satisfactorily explained, since there is no light down there to be iridescent in. Whale falls have turned out to be one of the more productive places in the ocean for describing species that were not previously known, and a fair number of them have been found on whalebone and nowhere else since. Then the crustaceans, tannaids, tiny and tube-dwelling. Isopods, which look like small marine woodlice and in the deep sea include some species that grow to a very respectable size. Amphipods again, the smaller resident ones this time rather than the swarms that came in the first months. Copepods everywhere, as copepods always are, since they are probably the most numerous multicellular animals on the planet. And the mollusks, limpets in several species, some of them living only on whalebone, snails of various kinds grazing the mats, the mussels and clams with their internal bacterial gardens. Overlying all of it, and easy to miss because it does not look like an animal at all, the bacterial mat. It repays a closer look, because the mat is not a passive coating. It is a structure, and a rather clever one. The bacteria that build it need two things that come from opposite directions. They need hydrogen sulphide, which is seeping out of the bone from beneath, and they need oxygen, which is dissolved in the seawater above. The two overlap in a thin layer, and it is only in that layer that the chemistry works. So the bacteria position themselves in it. Many of these species are filamentous, long chains of cells strung end to end, and they can glide, slowly, along a surface. And they use that ability to hold station in the narrow band where sulphide from below meets oxygen from above, adjusting their position as conditions change. Some species solve the problem another way, by growing long enough to reach into both zones at once, storing sulphide at one end and oxygen at the other, effectively bridging the gap with their own bodies. Inside the cells, many of them accumulate small granules of elemental sulfur, stored as a reserve, and it is these granules that give the mats their particular whiteness under a light. A mat on a whalebone glows in a submersible's beam not because it is producing light but because it is full of tiny reflective grains of sulfur, which means that when you watch video of a whale skeleton furred over in white, you are looking at a very large number of extremely small organisms holding themselves, with some precision, in a chemical boundary layer that is perhaps a millimeter thick. The brittle stars, meanwhile, are simply everywhere. Brittle stars are echinoderms, relatives of starfish, with a small central disc and 5 long, thin, flexible arms, and on many deep-sea floors they are the single most abundant visible animal. There are places on the abyssal plain where the sediment is covered in them, at densities of dozens per square meter, arms overlapping, the whole floor faintly moving. They gather on whale falls in numbers, draped over the bones, arms wrapped around ribs, and what they are doing there is a reasonable question. Some appear to be feeding on the mats, some on the small animals living among them, some on particles suspended in the water just above. Some are probably there because the bone is a hard raised surface in a landscape of soft, flat mud, and a raised surface is a better place to hold an arm up into the current. In the images from the Diamantina Zone, they are one of the most striking features. Old whale skulls on the Hadal floor with brittle stars folded across them, several to a bone, quite still, as they presumably have been for a long time and will be for longer. There have been attempts to watch all this continuously rather than in visits. Time-lapse camera systems have been left at whale fall sites, taking a frame every few minutes for months at a time, and cabled seafloor observatories in a few places now provide live video from the deep for years on end. The footage that comes back is mostly uneventful, which is precisely the point. It shows a scene in which small things move slowly and nothing much happens for weeks. And then, occasionally, something arrives. A large fish crossing the frame, an octopus settling on a rib and staying for an hour, a sudden increase in the mats after a change in current, the slow drift of sediment covering a bone by a centimeter over a season. It is the most patient sort of science there is, and it produces the most patient sort of data. And there is something quite restful about the idea of a camera sitting alone in the dark at 4,000 meters, photographing a whale's shoulder blade every 10 minutes for a year, whether or not anything is happening in front of it. Most of the time, nothing is. It is worth taking a moment to consider how much of this is going on at this exact hour. Somewhere in the North Pacific tonight, there is a gray whale skeleton in its second year, still with tissue on the heavier joints, hagfish coming and going through the sediment around it. Somewhere off the coast of South America, there is a fin whale in its 40th year, the bones soft and porous now, the mats thinner than they were, the muscles in their last generations. Somewhere under the Southern Ocean, where the water is colder still and everything runs slower, there is a skeleton that has barely changed since the 1990s. Somewhere, at this moment, a whale is sinking. The estimates suggest that at any given time there are hundreds of thousands of these sites scattered across the floors of the world's oceans in one stage or another, which sounds like a great many until you divide it by the area involved and discover that it works out to a very lonely scattering indeed. A few per 1,000 square kilometers in the busier regions, far fewer in the empty middles of ocean basins. They cluster where the whales are, which means they cluster along migration corridors, in feeding grounds, over the deep basins that sit beneath the productive stretches of surface water. If you could map them, and nobody can, the map would be a map of whale behavior rather than of the seafloor. Lines and blooms of skeletons following the routes that whales have been taking for a very long time, laid down on the bottom like the record of a habit, and that habit is old. Whales are mammals, and they came from the land, which is one of the odder facts in the history of life, and one that took a long time to establish properly. Their ancestors were four-legged animals, living around the water margins of a shallow sea, roughly 50 million years ago, and over a span of about 10 million years, which is quick for this kind of thing, that lineage went from wading to swimming to living permanently at sea. The fossil sequence documenting it is one of the better ones in the record, and it includes a series of intermediate animals that get progressively less able to come ashore. So there have been whales of some description in the ocean, and therefore dead whales sinking into it, for tens of millions of years, but not whales of this size. The truly enormous baleen whales, the blues and fins, and the rest of the giants, appear to be a relatively recent development. The evidence points to gigantism, arising in that group only a few million years ago, associated with changes in ocean circulation that concentrated their food into dense, patchy, seasonal swarms and made it worth being very large in order to exploit them efficiently. Before that, whales were substantial animals, but not the largest that have ever lived, which places a rather interesting frame around the Diamantina finding, though it should be held loosely, since the correlation is suggestive rather than established. The accumulation in that zone appears to reach back at least 5.3 million years. The rise of the great whales is thought to have occurred at roughly that end of the timescale. It is possible that what has been found on the floor of the southeastern Indian Ocean is, among other things, a record of the period in which whales became enormous, filed continuously ever since. The bone-eating and the chemosynthesis, though, are certainly older than the giants. Fossil whale skeletons have been found in rocks on land, in Italy and Japan and the western United States, with fossilized chemosynthetic clams still attached to them, preserved in place, showing that whale falls were functioning as sulphide-driven habitats tens of millions of years ago. And the distinctive borings left by Osedax have been reported in bones considerably older than any modern whale species, which suggests the worms were already at their work in the early history of the group. There is even a reasonable argument that this way of life predates whales altogether. Before the whales, there were other large marine vertebrates, the great swimming reptiles of the age of dinosaurs, and they too must have died and sunk, and their bones were also full of fat. Fossil sites have been described in which the remains of such animals appear to carry chemosynthetic communities. The evidence is thinner and more contested, as it usually is that far back, but the principle holds. Large bodies have been falling into the deep sea and being converted into small, temporary chemical ecosystems for as long as there have been large bodies in the sea to fall. The whale is only the current holder of the position. And when you put it that way, the whole thing settles into a slightly different shape. It stops being a curiosity about a dead animal and becomes something more like a feature of how the ocean works. There is a slow and continuous transfer of material from the top of the sea to the bottom, most of it as marine snow, some of it in enormous single parcels. The bottom has evolved, over an extremely long time, to make use of both. The snow feeds the general spread of animals across the plain, thinly and evenly and reliably. The parcels build cities that stand for 50 years and then go. Neither is more natural than the other. Neither is an interruption. This is simply the arrangement, and it has been running, in one version or another, for a very long time, which brings us, gently, to how it finishes. The fat runs out. That is the whole of the ending, though it takes decades to happen, and it happens so gradually that no single moment marks it. The reserve inside the bone is finite. It was laid down by a living animal out of food it caught at the surface, and every year that the sulfate reducers work through a little more of it, there is a little less remaining. The rate does not change much, because nothing down there changes much, and so the decline is long and even and almost imperceptible from one visit to the next. The first thing to go is the intensity. Sulphide production falls off, and the mats respond immediately, because a mat is only ever as thick as the supply allows. They thin. They retreat into the places where seepage is still strongest, the interior of the skull, the deepest crevices, the parts of the spine that are half buried and slowest to be drained. On a skeleton in its later decades, the bacterial covering is patchy rather than continuous. Pale streaks and islands on bone that is otherwise bare. The muscles stop recruiting. An established muscle may live for many years, and the last generation on a whale fall lives out its life quite comfortably on a declining supply. But the larvae settling from the water column find conditions less and less worth staying for, and eventually they stop settling. So the clusters age together and thin out. Empty shells accumulate in the crevices where the living ones used to be, and stay there, since there is nothing much down there to wash them away. Osedax finishes with the bone in its own way. A skeleton that has been worked over by these worms for years is riddled through, and once the organic content within reach is gone, the roots have nothing left to draw on. The plumes are not replaced, the tubes empty. What remains is a bone that is structurally quite different from the one that arrived, honeycombed and light, with the mineral scaffold still standing, but a great deal of what was inside it gone. At this point, the bone begins to fail mechanically. Ribs snap under their own weight where they arch out of the sediment. Vertebrae collapse inward. Anything sitting proud of the floor gradually comes down onto it. Video from older sites shows this clearly. Skeletons that have flattened into the ooze. The shape still legible but low, more outline than structure. And here there is a fourth stage, proposed but not universally accepted, and worth mentioning precisely because the disagreement about it is honest. Some researchers have suggested that once the chemistry has finished, the skeleton still has one thing left to offer, which is simply that it is hard. In a landscape of soft sediment stretching for hundreds of kilometers in every direction, a lump of mineral standing a few tens of centimeters above the floor is a genuinely valuable object, because there are many deep-sea animals that need something solid to attach to and spend their entire larval lives looking for it. Anemones and deep-water corals and sponges, and the crinoids, which are the feather stars, and which perch on a raised point and hold their arms up into the current like a fan. So the whale, in this reading, ends its career as a reef, not a chemical habitat anymore, just furniture, a hard place in a soft world, colonized by suspension feeders that have no interest in what it used to be. The evidence for this as a distinct and general stage is limited, and some workers in the field regard it as more of an occasional outcome than a phase that every whale fall passes through, which is fair. What is not in doubt is that whale bones on the seafloor do get colonized by attached animals of exactly this kind, and that in some places they persist as raised hard surfaces for a very long time after the last of the sulphide is gone. How long is a question of chemistry. Most of the hard parts that fall into the deep ocean do not last, and the reason is that the deep sea is corrosive to certain minerals. Below a certain depth, which varies between oceans and is generally somewhere in the region of 4,000 to 5,000 meters, seawater becomes undersaturated with respect to calcium carbonate, and shells made of it begin to dissolve. This is why the sediment on the deepest parts of the ocean floor is a red clay, rather than the pale carbonate ooze found higher up. The shells that rained down for millions of years simply went into solution before they could accumulate. Bone is different. The mineral in bone is not carbonate but a calcium phosphate, and it is markedly more resistant to dissolving under those conditions, which is why whale bones can lie on a deep seafloor for a very long time indeed, while the shells of things that died in the same water column vanish. Add to that the burial rate, which on an abyssal plain is roughly a centimeter of sediment every 1,000 years, and you arrive at the arithmetic behind the Diamantina Zone. A bone lying on that floor is not going to be covered over quickly. It will sit there, exposed, slowly weathering, for thousands of years before the sediment has crept high enough to matter, and even then it is only being buried, not destroyed. That is how a rift valley accumulates 476 fossil whales without any of them going away. For most whale falls, in most places, the ending is quieter than that. The bones grow porous and fragile, break down into fragments, and the fragments become smaller, and eventually the site is no longer a site. There is a slightly different color to the sediment if you take a core. There is a scatter of dark mineral pieces that a passing camera would not register as anything in particular. Perhaps a heavy bone from the ear region, which in whales is unusually dense and durable, and turns up in fossil deposits more often than anything else they leave behind. lying half in the ooze. And that is the whale, finished. 50 years or more after it arrived, and rather longer than that after it last drew breath at the surface, except that the material is not gone anywhere. It never is. It went into hagfish, and into the sleeper sharks that fed and swam away, and into amphipods that scattered back into the sediment across a wide area. It went into worms, and into their eggs, and out into the water column as larvae, most of which came to nothing, and a small proportion of which found another skeleton somewhere else and started over. It went into bacteria, and from bacteria into mussels, and from mussels into the animals that ate the mussels. It went into the sediment as buried carbon, and it will be there for a very long time. It went into the water as dissolved compounds that the slow, deep circulation has been carrying away for decades. And some of that water will eventually rise somewhere on the other side of the world, centuries from now, and reach the light again. The whale, in other words, was not consumed. It was distributed. Everything that was one animal at the surface of the sea is now spread out through the deep ocean in a few million smaller pieces, most of them alive. There are things about all of this that nobody knows, and it seems worth setting them down plainly before we let the whole subject settle, since honest gaps are more restful than false completeness. Nobody knows how long a whale fall really lasts. The 50-year figure is an extrapolation from measured rates, and extrapolations of that kind carry a good deal of uncertainty when the thing being extrapolated has never been watched to the end. Nobody knows how many whale falls there are. The hundreds of thousands figure comes from a chain of estimates about populations and mortality and persistence, each reasonable, each with error attached, multiplied together. Nobody knows how much difference Osedax makes to the timetable, or whether the answer is the same in every ocean. Nobody knows whether whale falls really did serve as evolutionary stepping stones for the vent fauna, or whether that is a tidy story that the genetics only partly supports. Nobody knows what is at the bottom of most of the world's fracture zones and trenches, because nobody has been to look, and nobody has ever seen a whale die at sea, follow it down, and watch what happened afterwards. Every account of the sequence, including this one, is stitched together from carcasses that were placed on purpose, skeletons found at unknown ages, samples in cold rooms, and a good deal of careful reasoning. It is a real picture, and it is very probably close to right. It is not a film of an actual event, because no such film exists. Set those down now. They are not problems that need solving tonight, and the sea is not waiting on any of them. Let us go back down one last time, and take the whole of it in one slow pass, and then let it go. Start again at the surface, in the dark, far from anywhere, the swell moving in long, low hills, the water very deep and very blue beneath, a whale that has come to the end of a long life, lying quietly on the surface, and then, in its own time, beginning to sink, down through the first 200 meters, where the last of the light is, and out of it, down through the twilight zone, past the lanternfish and the drifting siphonophores and the great nightly migration going the other way, past 1,000 meters, where the light ends altogether and the cold settles in for good, down through the midnight zone, the largest living space on this planet, mile after mile of dark water with almost nothing in it, the pressure building steadily and the temperature holding at 4 degrees, and then the floor, arriving softly, the long settling into fine gray ooze, and the haze lifting and drifting and coming quietly back down, the plume of scent uncoiling downstream, the amphipods leaving the sediment, the grenadiers turning into the current, the sleeper sharks, unhurried, arriving from a long way off, the hagfish coming up out of the ooze where they have been waiting, perhaps for years, for exactly this, months of that, then years, the shape softening, the ribs emerging, the flank sinking down, then the small things in the enriched ground, the worms in their thousands, the dark stains spreading through the sediment and slowly fading again, then the chemistry, deep inside the bone, out of reach of everything with teeth, seawater working in, oxygen used up, sulfate reducers settling to work on fat that was laid down in the sunlit ocean decades before, hydrogen sulphide seeping outward, day after day, year after year, the mats arriving, white and gold, spreading over the bone like frost, the mussels settling into the crevices with their gardens of bacteria inside them, the limpets grazing, the red plumes of the bone-eating worms standing up off the skeleton in their hundreds, roots reaching down into the mineral, dissolving away inward, bacteria doing the digesting, and dozens of tiny males folded into the tube of each female, which is as economical a solution to loneliness as anything in nature. Decades of that. the most stable address in the ocean. No weather, no seasons, no light, no hurry. And then the long thinning, with the mats retreating and the muscles aging out and the bones growing porous and coming down onto the floor. The hard remains standing a while as something for anemones and corals to hold on to, the sediment creeping up at a centimeter a millennium. And in one particular rift on the floor of the southeastern Indian Ocean, where the water is cold and still and the burial is slow, all of that repeated so many times, for so long, that the bones have piled up into a record 5 million years deep, waiting, apparently quite patiently, for somebody in a small metal sphere to come down with a light and notice. That is the whole of it. It is happening right now, in several 100,000 places, at every stage at once, in every ocean on the planet, and not one of those places is being watched. There is one part of this we have not looked at, and it seems right to end there rather than on the seafloor, because it is the gentlest part, and because it came first. Before any of it, there was a whale, not 100 tons of material. An animal, with a life that went on for a very long time and was mostly quite pleasant, as far as anyone can tell. It was born tail first, in warm water somewhere near the tropics, in the season when its mother had traveled thousands of kilometers to give birth in water too warm to feed in and calm enough to be worth the journey. It was helped to the surface for its first breath. It drank milk of an extraordinary richness, thick as paste, and it grew at a rate that has few parallels anywhere in nature, putting on weight by the hour, doubling in length within its first year. It traveled with its mother to the feeding grounds, in the cold, productive water at high latitude, where the summer sun comes almost all day, and the sea turns green with growth, and the krill gather in swarms that can stretch for kilometers and color the water pink from above. And then it fed, and kept feeding, every summer, for decades. The way the great baleen whales feed is one of the more remarkable pieces of engineering in the animal world. The whale accelerates towards a swarm, opens its mouth to an angle that seems impossible for anything with a jaw, and takes in a volume of water that can exceed the volume of the whale itself, the pleated throat expanding enormously to hold it. Then the mouth closes, the throat contracts, and the water is forced back out through the plates of baleen hanging from the upper jaw, which are made of the same material as your fingernails and fray at the inner edge, into a dense mat. The krill stay behind, and the whale swallows, and then after a while it does the whole thing again. Each of those lunges costs a great deal of energy, and returns rather more. And a large whale may do it hundreds of times in a day through the feeding season, and put on a quantity of blubber that will carry it through the months when it does not feed at all. Then, in autumn, the long swim back towards warmer water, then back again in spring, year after year, up and down the length of an ocean, on a route that the animal seems to hold in memory with considerable precision, and through all of it, sound. The great whales live in a world where sight reaches perhaps tens of meters, and sound reaches across a basin. The low-frequency calls of fin and blue whales are among the loudest sounds made by any animal, and they are pitched so low that a human ear at close range would feel them more than hear them. In the deep ocean, there is a layer where the speed of sound reaches a minimum, and sound entering that layer tends to be trapped in it and can travel enormous distances, hundreds, or in some conditions thousands of kilometers, before it fades. So a whale calling in the middle of an ocean at night is, in a real sense, present across a very large area of it. Whether the calls are used to keep in contact over those distances is still argued about, and the honest position is that we do not fully know what the calls are for or how much of what is said is received, but the physics is not in doubt. The sound goes a long way, which means the animal spent 50 or 80 or 100 years in a world that was dark and cold and enormous and full, at all times, of the voices of other whales, some of them near, some of them a week's swim away. It knew the same routes and the same seasons for its whole life. It may have known individuals. It certainly knew its own calves and stayed with each of them for as long as they needed and let them go. And then, one year, somewhere out in open water, it grew old and the swimming became harder. And one afternoon or one night, quietly and without any particular event, it stopped and began the long journey down that we have followed all evening. There is no sadness in it that the ocean recognizes. The animal had a good deal of time and used it, and what happened afterwards was not an ending, so much as a handing over, the largest single gift the deep sea ever receives, delivered once and spent slowly, over half a century, in the dark, by things that would never otherwise have had it. So, let us come back up now, slowly, the way the submersibles do, with nothing to steer and nowhere to be. Up off the floor first, and the skeleton going out of the lights beneath us, the pale ribs and the mats and the red plumes fading back into the dark they came out of, and the whole sight closing up behind us as if nobody had been there. It will not miss us. It has no use for observers. It will keep doing what it is doing for another 30 years, whether or not anyone ever comes back. And it very likely will not be visited again in your lifetime or in mine. Up through the midnight zone, the pressure easing by a little every minute, the temperature holding, the dark absolute, up past 3,000 meters, and the occasional soft flare of something living making its own light out there beyond the ports, up past 1,000, where the first suggestion of the sun begins to reach, so faint that the instruments notice it before the eye does, up through the twilight, and the blue coming back into the water, dark blue, then less dark, then the blue of an evening sky, and out, finally, into a morning at the surface, with the swell moving in long, slow hills and the light coming across it, and 4,000 meters of quiet water underneath, going about its business. Now let the sea go, and come back to the room. You are lying somewhere warm and dry, on a soft surface, with a certain amount of weight resting into it. There is a ceiling above you rather than 4 kilometers of water. There is air, and the small, ordinary sounds of a building at night, and the temperature of a room that has been holding its warmth all evening. And the frame of you is still there, pressing gently down. The heels, the backs of the legs, the hips, and the length of the spine, and the shoulder blades laid flat, and the back of the skull settled into the pillow. Warm bone, living bone, being quietly rebuilt and dissolved and rebuilt again while you lie there doing nothing whatever about it. That was where we started tonight, and it is a good place to finish, because it is the same fact at both ends. A skeleton is not a dry thing. It is a store and a scaffold, and it is one of the slowest and most patient parts of any animal, and it goes on holding its shape long after everything else is let go. Let the weight settle a little further. There is nothing that needs holding up now. Let the shoulders come down away from the ears, if they have not already, and let the jaw be loose, and let the hands lie wherever they have ended up. Somewhere out there tonight, at this hour, in water 2.5 miles deep, there is a skeleton on the seafloor covered in soft white mats and red plumes, in complete darkness, at 4 degrees, doing its slow chemistry. There is another one, 1,500 kilometers away, in its first year, with hagfish moving over it in the ooze. There is another in the Southern Ocean that has hardly changed since before you were born. There is a whale sinking through the twilight zone right now, unwitnessed. An hour into a journey it will finish before dawn. None of it is urgent. None of it requires anything from you. It has been going on for tens of millions of years without a single person watching, and it went on all through last night while you slept, and it will go on all through tonight in exactly the same way, patient and cold and entirely unhurried. So there is nothing left to do with any of it now, except let it go. Let the images go, one at a time, in whatever order they want to leave in. The red plumes on the vertebra, the white mat standing out in the lights, the long broken line of the spine on the gray floor, the skull, half buried, with the brittle stars folded over it, the submersible lifting away and the whole sight closing back into the dark behind it. Let the numbers go. The 7,000 meters, and the 476, and the 5 million years. They will keep perfectly well without being held onto. Let the water go, mile after mile of it, cold and still and immensely deep, and let it be down there rather than here, and come back to the small warm space you are actually in. The weight of the blanket, the shape of the pillow under the side of your head, the temperature of the room, the slight, ordinary sound of your own breathing, which has been getting slower for some time now without any help from you. Warm bone, holding you together, doing its patient work in the dark, exactly as it has all your life and exactly as it will while you sleep. You can stop listening whenever you like. There is no ending you need to stay awake for. Nothing after this point is important, and if you drift off in the middle of a sentence, that is precisely what this was made for. Somewhere tonight, a whale is settling gently onto the floor of an ocean, and a haze of pale sediment is lifting a meter or two, and then drifting, and then coming quietly back down. Sleep well. The sea keeps its slow watch in the dark, and it will still be turning, far below, long after the light has gone.